Good afternoon. Thank you for coming to this interesting experimental concert that we're having. Elaine Chew was organised with our collaborators here. Peter Taggart and I are both cardiologists. We study abnormal heart rhythm problems and the effect of the brain and the heart on the heart. And Jane Eyre and James Weaver, who's helped us with this today. So I thought I'd just start with a quick talk, just for 10 minutes, to give an outline of some of the research we're doing, supported by the Barts charity, and also just to give you some insight into why a cardiologist is standing in a church talking about music. The heart is an electrical pump. It actually has electrical energy, and this was actually worked out about 200 years ago by two German physiologists, and they actually connected a heart to a frog's leg. So they recognised that electricity made muscles contract, and they tried an experiment one day when they took a frog's leg and connected it to a heart, and the leg started kicking, and they recognised that there was actually electricity coming from the heart. And this is a physician. He was a doctor actually at the Royal Free Hospital called Augustus Waller, and he recorded the first ECG heart tracing in a human being. And the reason I'm putting this slide up is that unfortunately cardiologists, we've got a bit of a reputation of being a little bit arrogant, and he was probably the most humble doctor, certainly humblest cardiologist I can think of, and that he wrote, "I do not imagine that the ECG, the heart tracing, is likely to find any very extensive use in the hospital. It may be used for very rare anomalies of the heart." So it's the most common test we use in the hospital, and it's interesting to think that he was so humble. So when we record from the heart, we record electrical waves, and these give us information about the electrical activity in the top chambers and the atrium, which corresponds to the P wave here on the ECG tracing. And then this large spike here, which is the QRS complex, corresponds to the contraction of the ventricle. And this part here is called the T wave, which is the electrical resetting of the heart. Now we have lots of very clever ways of studying the heart electrically. We can actually, when a patient's having an open heart operation to have a new valve or a bypass operation, we can actually put a sock on the heart and actually record electrical. I'll point at it because it's easier. We can put a sock on the heart with lots of electrodes and record information from the heart, but that's obviously not very practical. We can also, when patients are having procedures, put catheters inside the heart and record electrical activity. And this is just to show you just how well coordinated the heart is. The top maps are electrical maps of activation, waves of electrical activity moving through the heart, and the bottom is an MRI scan and the electrical waves superimposed on it. So the heart is electrically and mechanically very closely coupled, very closely associated. Now, we've been doing a lot of research trying to understand the electrical activity of the heart without actually touching the heart, without having to put tubes in the heart and so on, by using a special jacket called an ECG imaging jacket, which is on the left there. It's a very expensive waistcoat, costs about £1,500. And we can place this jacket on the surface of the patient's chest, and that can actually take a picture of the electricity moving around the heart. And that's really helpful because we can use it to target our treatments or plan our operation before the patient goes to the operating theatre or to the cath lab. But it also means that we can study the electrical activity of the heart as well. And this is on the right-hand side is a patient having extra beats, and the white area is the area where the extra beat is coming from. And sometimes it's very difficult to know where these beats are coming from, and we may have to wait 4, 5, 6 hours for just one beat to occur. So with this technology, we can actually see where it's coming from straight away, or put the patient on the ward and wait, and then target the treatment in the lab. The other very common heart rhythm we deal with is this heart rhythm called atrial fibrillation. So the patients would feel this with an irregular heartbeat. They may feel breathless or dizzy. And over the age of 60 years, we find it in about 2 or 3 in 100 patients. And over the age of 70, it's about 1 in 20 people have atrial fibrillation. And this rhythm, if you look at the heart tracing here, and I appreciate some of you aren't medical, so you'll see that there are lots of erratic waves here, chaotic. It's chaotic activity. So when we use this jacket, I'm just going to come out of this slide. This is when the whole computer crashes, so we'll just see. When we actually use the jacket to study these irregular electrical activity, you might appreciate that there's actually a little circuit here. There's electricity moving around in circles in one area. So we think that could be the origin of this irregular activity, and here as well, there's another one. So we're very interested in seeing where these regions are so we can then target the treatment. And my colleagues at Barts are studying these maps to see if we can improve treatment to target treatment in this very common irregular heart rhythm. Let's see if that works. Now, we've got the World Cup coming up on Thursday, and you might be interested to hear that football can actually be bad for your heart. So this is a graph that's actually showing the number of people that had a heart attack during the World Cup in Germany. So the red spikes are during the World Cup in 2006, and because this is scientific, they looked at the years before and after. And you can see not much is happening. Well, there are events, but not that many. But suddenly in the World Cup, exactly the time when the West German team was playing, there were a lot of people having cardiac arrests and heart attacks. And these spikes here correspond to when there were penalty shootouts. So the stress of watching the football triggered cardiac arrest. And you can see here that actually Germany didn't get all the way to the end because after this people lost interest. So after they got knocked out of the quarterfinals, that was it. So why is this important? Well, the thing is we have this issue. We know that stress can make your heart speed up, and we know that stress can cause heart attacks, but how does that happen? Why does it happen? And the heart has got a very rich innervation. There are many nerves around the heart. There are over 10,000 nerves around the heart. Some are special nerves from the vagus, which slow the heart down, and others are from the sympathetics that contain adrenaline, which make the heart speed up. And actually, of course, these nerves are connected to the brain, and actually the left and the right sides of the brain innervate the heart in a slightly different way. And the left side of the brain innervates the back wall of the heart, and the right side of the brain innervates the front wall of the left ventricle. Now this gets really interesting because, of course, if you have certain emotions like anger or happiness or fear, they actually come from they actually can be mapped and derived in certain areas of the brain. So anger, fear, and happiness come from the right side of the brain, and in being serious comes, or thoughtful, comes from the left side of the brain. So this means that we can actually then perhaps look at the relationship between the regions of the brain and the activity in the heart. And the way we can do this is that if a patient is having a procedure in the cath lab, having a procedure for their heart rhythm problem, we actually can put wires in the heart and record the electrical activity, because that's part of their procedure, where we can get extra information. And these wires give us electrical information about the behaviour of the heart, and this is work that Peter Taggart did at St Thomas's Hospital, because we were interested in what happens when you stress a patient. And one way you can stress a patient is to show them a scary movie. So here we have an engineer and a patient and a television screen. So the patient's watching the film, and we're recording from their heart at the same time. And the film that we showed them was The Vertical Limit, which, I don't know, has anybody seen The Vertical Limit? It's a mountain climbing film. And of course, at one point, there's a very attractive young lady hanging by a wire, and she might fall at any moment, so she has to be saved. So there's a lot of dramatic music and drama going on. And then you can actually record the electrical activity in the heart, and also you can record how anxious the patient is. And so this is how much they sweat, which is a measure of their sympathetic drive, the adrenaline in the body. This is their respiratory rate. And actually, when we record from the heart, we can actually record the changes in their electrical resetting. We see a change also in the electrical resetting of the heart at the same time, their repolarization. So there's a direct effect of the nerves on the heart on the electrical activity. The other issue is that actually when you study the brain with PET imaging, so this is imaging the brain, the red areas are the increased blood flow in the brain when that area of the brain is active. And this is actually playing music, which is supposed to be music that makes you feel happy and jolly, and different regions of the brain are lighting up that make you feel, that correspond to that music. So Elaine and I met about a year and a half ago, and knowing that she was a professor of digital music, we spent about 6 months sort of discussing how could we look at the effects of music on the heart. Is there something we could actually pick up the effects of the electrical activity of the heart in music? And of course, music has its own internal rhythm, just like the heart has its own rhythm, and actually the nervous system has its own rhythm. And are there transitions in the music which may affect the electrical activity of the heart, or there are effects of music on your emotions that we can actually measure? So we took some patients who have pacemakers, and of course the great thing about a pacemaker is that there's a lead inside the heart and it's recording electrical activity at the same time, so we can study that. So we took some very helpful patients who have a pacemaker, and we can put a program, a device on, we can record from their pacemaker, and we took them in the church there just at the back, and Elaine played them some music, some different musical pieces, and you can see they're all sitting here, and we have Holly here, one of our physiologists who helped us, and some of the other members of the team who allowed us to record during the playing this music, so we can then see the effect of the music on the electrical activity of the heart. So at the moment we're analysing those results, so maybe in the future, not too far in the future, I'll be able to show you what we found. But that's enough of me talking. So this work is partly funded by the Barts charity, and also in collaboration with the patients at the Hospital Barts Heart Centre and the team here. So Elaine's going to play some different pieces. I'm probably going to get this all in the wrong order, but some of the pieces you'll recognise. And then she's taken the ECGs from the patients and looked at the intervals of the beats and the changes in the intervals of the beat, and then she's going to play the music dictated by the rhythms within the ECGs from different patients with abnormal heart rhythms. Some of them will be a regular heart rhythm, a ventricular tachycardia, for those of you who know what that is, a fast racing of the bottom chamber of the heart, and some of them will be the irregular heart rhythm, the atrial fibrillation. Right, Elaine, take it away.